All right, so this is example 2 from class, and I want to note before we even get started, there's a typo in the problem. It says 97 million was the population in 2010. It's intended to say 9.7 million, so if you'll go ahead and change that, that would be great. 9.7 million. All right, now, this is talking about population growth in the state of Georgia, and anytime you have a population that's growing, it grows like on a continuous basis. It's not like a quarter goes by and suddenly the population jumps by 100,000. So whenever you see a population growth problem, you're usually going to be using the continuous growth formula. But it's not money, so we're going to use the generalized one, which is y equals n times e to the kt. Y is the final population or the final amount, n is the initial population or amount, e is the number e, k is that relative is called a growth or decay constant, but it's also called the relative growth rate, and t is time. So this problem tells us that in 2015 the population was 10.2 million, in 2010 the population was 9.7 million, and we want to determine the value of k, which is the relative rate of growth. So below the formula, I'm going to write out all my variables. In 2015, the population was 10.2 million. So at the end of the time I'm looking at, the population was 10.2 million. So I'm going to write 10.2 for my y. Now I could write out million, but I'm just going to treat this as if all the populations are millions and deal with the smaller numbers. In 2010, it was 9.7 million. So we started in the time period which we're looking at with 9.7 million. So that's n. And then over the course of this beginning and end, 5 years passed. It went from 2010 to 2015. So my time here is 5, and k is what I'm looking for. So I'm going to plug everything in. And you're going to see that solving this is remarkably similar to what we did in the last example. So I want to solve this for k. It's in an exponent, so I'm going to have to end up taking a log of both sides. But before I do that, I need to make sure I solve my reverse PEMDAS. So I'm going to undo the multiplication first. And then that 10.2 divided by 9.7 isn't a pretty number, so I'd probably find that in my calculator and store it. Let's call that A. And now I can focus on solving. So I'm going to take the ln of both sides. I choose the ln here because I have a base of e. I could use the common log if I wanted to, but it's just easier if you use the natural log. That allows me to kick the baby. And then ln of e is log base e of e, so it's asking what power you raise e to in order to get e. That's 1, so I'm just going to mark that out. And that means that k is ln of a divided by 5. So I'm going to plug that into my calculator, and I'm going to get 0.01005. Now, when you're working with exponential stuff and you find things like k that we're going to use again in part B, I don't want to round it because it'll throw my answer off. So I'm going to take that number I just got and I'm going to store it. Now, I'm going to be clever. I'm going to store it as k in my calculator, so it's used as the same thing. So in part B, the problem says, in what year will Georgia's population reach 12 million people if this growth rate continues? So when we talk about growth rate continuing, that means that the k we just calculated is going to be the same in this part of the problem. So I have y equals ne to the kt, y n k t. My k is that constant k I just calculated in part A. Now, if I want to know when the population will reach 12 million, so that's my final, it's 12. And then for my n and my t, I have choices. I can either choose the n that was from 2010, and if I calculate the t there, that would be the number of years from 2010, or I can let my n be the calculation from 2015, and then my t would be the number of years from 2015. I tend to use the initial value from the original problem, so I would use 9.7 in 2010, but it's not going to matter which one you use as long as you answer the question appropriately at the end, and we'll talk about that at the end. So I'm going to use 9.7 as my initial, and then my t is going to be the number of years, and it's going to be from 2010 because I'm using the population from 2010 as my start. So I'm going to plug everything in. trying to solve for t. So I'm going to divide both sides by 9.7. I'm going to take the natural log of both sides. I'm going to kick the baby. Natural log of e is 1. So my t is going to be this number. So when I punch that into my calculator, I get 21.16. Now the problem didn't say how many years from now would it happen. It said in what year. So I started in 2010. I'm doing 21 and some odd years. So I'm going to end up in the year 2031. Now, if I had started with a population of 2015, the answer I would have gotten would have been about 16 and some change. And so my year still would have been 2031 because it would have added that number of years to the year in which I started. All right, so part. So this doesn't have a t in it, so I'm going to leave it on this side. 9.7 divided by 11.6. And I really could have done 9.7 divided by 11.6 and stored that. That probably would have made the work prettier. And I'm going to move the kt to the other side. That allows me to factor out the common factor of t. And then I can divide both sides by that thing that's being multiplied by t. That's an ln. Wow, that's just the worst L. So ln of 9.7 divided by 11.6 divided by 0.004 minus my value of k. And that would be my time. So I would plug that into my calculator. And I would be careful to remember to group the thing in the bottom in parentheses so my calculator does it correctly. And when I do that, I get t equals 29.555. So that means 29 and some change after my initial population, which was 9.7, which was in 2010. Georgia's population will pass Ohio's. So that means basically sometime in the year 2039.